working through the class test for Form 4 Electrostatics. Multiple choice question 1. Electric force per unit charge experienced by a small test charge is defined as electric field strength. That's just the definition of electric field strength specifically. So 1.1 will be B. Question 1.2 says two metallic spheres, each carrying a charge of Q, are a distance r apart. Which one of the following pairs of changes will double the electrostatic force? So which one of the following pairs of changes will double the electrostatic force, which is F, that one sphere exerts on the other? This is a multiple choice question, but it's going to require some calculations from us. So let's just quickly pop up over here so we can do the calculations alongside with that. If they say, option A, the distance is decreased to r over 2 and you double the charge in both spheres, we can calculate the change by using the formula of Coulomb's law and then just calculating it for each option, the force. So the first force will say that, okay, what happens to the force? K stays the same, that's a 1. The distance has decreased to r over 2, so that's going to be half, and we square it, multiplied by the charges are doubled on both. So we get 2 times 2 is 4, over a half squared, which is a quarter. So it's just 4 over a quarter, which gives us 16. So the force will be 16 times stronger for option A, so it cannot be A. We repeat the same for B, where they say we decrease the distance to r over 2 and reduce the charge on one sphere to Q over 2, so we're halving one charge. So K stays the same, one charge is halved, another charge stays the same, and the distance is halved again. Remember to square it here. Then at the top we have a half, at the bottom we have a quarter, and that gives us 2. So we don't even have to check options C and D, although you can, just to go check for yourself which answers you get. But the one that doubles will have to be B. So it's 1.1 B, 1.2 B. And that's our answers for question number 1. If we go over to question number 2, which is Form 3 electrostatic work, they tell us two small identical spheres have a charge of plus 10 microcoulombs and minus 14 microcoulombs respectively, hung a certain distance apart. Alright, so to assist us with this question, we can draw question 2, we can draw a nice diagram, and that will assist us with the calculations as well. This is my 10 microcoulomb, and it's a positive charge, and this is my minus 14 microcoulomb. Okay. I'm just going to call them A and B for simplicity. That's our scenario. They're allowed to touch, then move back to their original position. So they're a certain distance apart, right? They're a distance apart. Then they come into contact with each other, A and B, and then electrons are transferred. Electrons will transfer from the more negative one, so when they touch, electrons will be transferred. And then we end up with them back at their new position, still a distance of x apart, A and B, but now they have a new charge after the transfer of electrons occurring there. And that is the scenario that they've given to us. And lastly, let's say the size of the force between the two spheres after they touch is 0.007 newtons. So the force in this area is 0.007 newtons, which we're only able to use after they've touched. Now question 2.1 says, calculate the charge on each sphere after they have touched and then moved back to their original positions. It's 2 marks, so for us to answer question 2.1, this is where we're going to answer it. We can say Q final is equal to Q1 plus Q2, and we divide it by the number of spheres that we have, so it's divided by 2. So we can say this is 10 microcoulombs, and we add the negative 14 microcoulombs, all of that over 2, which gives us 10 minus 14, and we get 2 times 10 to the negative 6 minus 2 times 10 to the negative 6 coulombs, because remember we have to convert the micro through. So that's our answer for the first one. That is our Q final that we've calculated. That means that is the charge on these spheres after they've touched. So now they have a charge of minus 2 microcoulombs and minus 2 microcoulombs on both of these spheres. That's what we end up having there. Question 2.2. How many electrons were transferred from one sphere to the other? For calculating the number of electrons, for question 2.2, then we have to use the formula of N is equal to delta Q, or Q over QE. And to use this formula, we must first calculate delta Q, which is Q final minus Q initial. And you can substitute this directly into the formula. I'll write it here. Q final, I'm going to take the final charge here at the end. Remember, this is the initial charge, and here we have our final charge. And if you calculate the Q final minus the Q initial, then we can take the second option. You can choose either one, doesn't really matter. You can say minus 2 times 10 to the negative 6, which is my final charge here. And I'm going to subtract the initial charge of minus 14. So minus 14 times 10 to the negative 6. And I take all of that over the charge of an electron, which is 1.6 times 10 to the negative 19. And we put all of that into our calculator. We have a value of 7.53 times 10 to the 13 electrons. And that is how we calculate the number of electrons. We're taking the change in charge over the charge of a single electron, and we get our number of electrons transferred for 4 marks. Lastly, for question 2, we have to go to question 2.3, which says the following. Determine how far they were originally from one another. So they're asking, what is this x, excuse me, this distance there? If the force is 0.007 newtons, what is the distance? And for us to use that, we must use Coulomb's law. Write down your formula, kq1, q2 over r squared. And we substitute the values that we have. But remember, this is after they have touched. So when they have a charge of minus 2 microcoulombs, they have a force of repulsion of 0.007 newtons. So I substitute 0.007. K is a constant, 9 times 10 to the 9. Q1 and Q2, that's 2 times 10 to the negative 6. And I'm going to square that, since it's just the two of them, squared. And we take that over r squared. And we could complete the maths where you square root at the end and get a value of 2.27 meters between the two spheres. And that's our answer for question 2.3. Let's take a look at question 3. Three charged spheres ABC are aligned as follows, and they're in a straight line. First, nanocoulombs. Remember, nano means times 10 to the negative 9, and we must convert centimeters to meters. So you can take centimeters to meters by dividing by 100 to calculate that distance. Question 3.1, state Coulomb's law of electrostatic force in words. You can get that straight from your notes. Very important to have all the key terms in there. So make sure you have all of the key terms for Coulomb's law of electrostatic force when you answer this question. Question 3.2, calculate the net electrostatic force that sphere B experiences. Alright, so now we're thinking about sphere B and what force it will experience. If we calculate force, we must use our force formula. And it's experiencing a force due to these two spheres on either side. So, let's take that and answer our question. Question 3.2. I'm first going to calculate the force of A on B. So FAB is K Q1 Q2 over R squared. And we quickly substitute those values in. 6 times 10 to the negative 9 times 2 times 10 to the negative 9. Remember, we don't concern ourselves with units, positive or negative. That just gives us the direction of our force at the end. And the distance is 4 centimeters, so it's 0.04 meters, which we squared. And you get that by dividing by 100. And we can say the force of AB. We complete that calculation, and we end up with a value of 6.75 times 10 to the negative 5. And very important here is that it's in units because we're calculating a force. Now A and B are both positive, so it will be a repulsive force on B. So you can say the direction will be right or towards C. Either one is acceptable. Then we have to go calculate the force of C on B, and we do the same, KQ1, Q2 all over R squared, and we substitute those values in. Once we've done that and we've converted the distance to 0.12 meters squared, we end up with a value of force CB of 1 times 10 to the negative 5 newtons, and the direction for that one, positive and positive, they will repel each other, so B will be repelled to the left. That will be my direction for this section. We have that, and that's the two forces that sphere B is currently experiencing. But they're asking for the net, meaning the resultant, or the sum of the two. So we can go calculate F net by saying that's going to be FAB plus FCB. And if we have that, we can go substitute the values, and since they're in opposite directions, we will subtract the 1. So I'm going to say 6.75 times 10 to the negative 5 plus, and since it's in the opposite direction, I'm going to subtract FCB. So minus 1 times 10 to the negative 5, they're in opposite directions, and we can then see that our net force will be 5.75 times 10 to the negative 5 newtons, and the greater force was to the right, so our resultant force is also to the right, which we have right there for question 3.2. And that is your answer. We move on to question 4, which is electric field questions. And they say 2 point charges of positive 8 nanocoulombs and negative 4 nanocoulombs are placed at points A and C respectively, which are 80 millimeters apart. So important to remember, and I did it in the previous question, nano is times 10 to the negative 9, and we must convert millimeters to meters. So how do we do that from millimeters to meters? Remember, we divide by 1,000, a factor of 1,000. So this is our setup that we're dealing with here. They're 80 millimeters apart. The question then states, define the term electric field. For us to define that, you take a look at your notes, make sure you give it proper definition with all the key terms in there. Remember, if you have anything missing, you lose marks for your definition. Question 4.2, calculate the net electric field intensity. Now, if we see the term electric field intensity, that refers to E, electric field strength. So we need to know that we can use the formula of E, K, Q, R squared. That's our formula for electric field at a point, or electric field strength at a point. And they say calculate it at point B, which is midway between A and C. Okay, so for us to answer that question, now we're going to just take a look at this right here. We have to quickly go and, for 4.2, I'm going to draw my setup. So I'm going to just copy this so we can keep a nicer eye on it. We have A, B, right there, and we have C. Okay. And they say it's halfway. So this distance was 80 millimeters, which means 40 millimeters and 40 millimeters individually, or respectively. Let's take a look at what they're asking. Calculate the net electric field at this point, and this will be done by using E due to A is K Q R squared. Substitute, it's 9 times 10 to the 9 times A. A has a value of 8 nanocoulombs, so 8 times 10 to the negative 9. All of that over 0.04. Remember, we have to convert 40 millimeters to meters, so dividing by 1,000, 0.04 squared. And then we get EA. We put that into our calculators and get a value of 45,000, and important here is the units, newtons per coulomb. Remember, electric fields also have direction, and since A is a positive charge, right, positive and negative, a positive point charge, the direction away from a positive will be to the right or towards C. So I'm going to say towards C, or you can say to the right. We can also go quickly calculate E due to C with KQ over R squared, and that gives us 9 times 10 to the 9. C has a value of 4 times 10 to the negative 9 all over 0.04 squared. Make sure you convert those distances. Once we substitute that into our calculator, we see that the value we get is 22,500 newtons per coulomb, and the direction is, once again, since this one is negative, the electric field lines is towards the point charge, so it's to the right or towards C, so that both of these electric field strengths are in the same direction, towards C. So we have the one, we have the other, and then we have to calculate the net force. So we can say E net is EA plus EC, and we add 45 to 22,500, 45,000 plus 22,500, and we get a value of 67,500 newtons per coulomb, and it's towards C, or to the right, towards C. And that is question 4.2 answered for us. We continue to the very last question, which is question 4.3. Calculate the magnitude and direction of the force experienced by an electron placed at point B. So very important, magnitude, how large is it, and the direction by an electron. So remember, an electron has an elementary charge of 1.6 times 10 to the negative 19 coulombs, a value which will be given to you or is given to you. And to calculate the force experienced by a charge in an electric field, for question 4.3, we use the formula E is equal to F over Q. Okay. We've just calculated our electric field strength is 67,500. They want the force, so we leave F open, and Q is an electron, which is 1.6 times 10 to the negative 19. We rearrange that, multiply 67,000 with 1.6, and we get a value of 1.08 times 10 to the negative 14 newtons. Now also what they're asking for is the direction. Remember, this is an electron. An electron has a negative charge, and negative charges go opposite to the direction of our usual electric field lines. So we can say it won't be towards C, rather it will be towards A. And if we go think about it as well, take a look at this setup. This is positive and this is negative. If I place a negative electron here, which direction will it move? It will be repelled by the negative one and attracted by the positive charge. So we expect it to move from right to left, or towards A.